let's examine a classic inductor. And put all of its parts on the table in the appropriate boxes. So we'll start here with our classic formula: V equals mu naught N over H I naught. And then we know that flux B equals B times the area, where the area is N times pi R squared, from our cylindrical geometry of the solenoid. And so then we can write flux B is mu naught N over H N pi R squared. But we can also multiply it by 4 pi over 4 pi and get a slightly more instructive form out here. 2 pi r n squared over 4 pi h. And there's a not here. We recognize now it's wire length squared over 4 pi h, so that's a good thing. We'll put that in here. Mu naught 2 pi r n squared over 4 pi h I naught. Okay. Now we know that V equals d flux B dt. So we can simply say that it's 2 pi r n squared over 4 pi h di naught dt, because the only thing that changes with time is the current. The geometry remains fixed. So we can write V as mu naught 2 pi r n squared over 4 pi h di naught dt. Okay, now we know that V equals E times the distance. The distance in question now is the length of the wire, 2 pi rn. So we can write then that E equals V over 2 pi rn, and that leads us to a simple expression, mu naught 2 pi rn over 4 pi h dt. Put that in here. Mu naught 2 pi r n over 4 pi h di naught dt. And now we know that flux E equals E times an area. And the area in this case is the surface area 2 pi r h, because that's the area over which the E field is distributed. And that allows us to write flux E equals mu naught 2 pi r n squared over 4 pi n di naught dt. And we'll fill that in this box here. It's mu naught 2 pi r n squared over 4 pi n di naught dt. And at this point, we can recognize that when we went from B to flux B, we gained a factor of n pi r squared. And when we went from E to V, we gained a factor of 2 pi r n. And so we can then conclude that if we go from B to Z, we better gain a factor of n pi r squared over 2 pi r n, which is just r over 2. And r over 2 is just the ratio of the area over the circumference for any circle. Let's see, we already knew this one was 2 pi r n. Now, the question arises, what's this line represent? And we can do the same trick again. We know that we went from E to V by gaining a 2 pi r n, and we went from E to flux E by gaining a 2 pi r h. And this tells us now that when we go from V to flux E, we need to gain 2 pi r n, 2 pi r h over 2 pi r n, which is h over n. So this line here must be labeled h over n as we go across it this way. And h over n we see came from the surface area over the wire length. Now, if we go back to our original B here, we have B equals mu naught n over h I naught. We see that we should probably put back our factor of 2 pi r over 2 pi r so that we have wire length over surface area. And this makes keeps our mind on the physicality of the situation. So we'll just write in our 2 pi r's here. Okay, now let's see. Now we have enough information that we can fill in all of the boxes on the chart, because these boxes differ from this one only by time derivatives. So these use di naught dt, this one will have I naught, this one will have q naught, and this one will have the second derivative of I. And otherwise it's the same constant, mu naught 2 pi rn squared over 4 pi n. And that constant also carries over here. In this row, it's going to be this constant carries over everywhere. Mu naught 2 pi rn squared over 4 pi h with q naught. This column, everything will be q naught. Here, everything will be I naught. Here we get di0 dt. And here we'll have a second derivative. And then the constants, again, when you take this constant, it goes all the way across here, mu naught 2 pi rn over 4 pi h. And here we have mu naught 2 pi rn over 2 pi rh and the q naught. Okay. And the chart does extend in all directions. You can use the same trick we did to define these distances to extend down here toward volumetric density and other directions on the chart as well.